Okay, so here's a video about 3.1. Um, so just for an overview, in section 2, or is chapter 2, we already talked about derivatives. But in that chapter, we were doing it what I would call the hard way. We were finding f prime of x, and if you remember, this is the limit as h goes to 0, f of x plus h minus f of x over h. And every time in the past, every time I wanted to find the derivative of something, I had to really do this limit, and I had to do all this algebra to cancel the h and find the limit. Now in chapter 3, we're going to learn several shortcuts for this. And in section 3.1, we learn our first shortcuts. So we're going to find a bunch of derivatives today without actually calculating this limit. By the way, so I'm about to state some of these rules, but let me describe the notation. So this d over dx, you've probably seen it in the book. That just means the derivative of whatever is in brackets. In other words, if I write d of dx and then I write a function in here, this means the same as f prime of x. That's just the derivative. And it's the same thing that we've been talking about all along. It's this limit, although we're not going to have to go through the work of finding the limit anymore. So here's these rules in these boxes. And for this, let's assume that the numbers a, b, and c are constant. So a could be like 2 is a constant, b could be like 10 is a constant. Things that are constant, there's a lot of things that are constant, like pi is a constant, e is a constant. So these are just any constants. Anyway, the derivative of a constant is 0, which makes sense. The derivative of a function is like the slope of the tangent line, and if you've seen the graph of a constant function, it's just a function that is completely flat. It is a horizontal line, so it would have slope of 0. Anyway, here's the other derivative rules. To do the derivative of a power of x, what you do is you take this power down in front, and then you reduce the power by 1. So that's the derivative of a power of x. There's also, maybe I'll skip this one for right now, the derivative of e to the x is itself. That's a function that is its own derivative. And up here we have a rule that can allow us to combine derivatives. If I have a constant times a function, maybe plus another constant times another function, basically it's very easy. This constant just stays the same, and I do the derivative of f. So it goes a and then f prime. And then similarly I do b and then g prime. That's this. Okay, so let's use these rules. And by the way, so the instructions just says differentiate. Differentiate means find the derivative. We don't use the word like derivate or anything like that. It's called differentiating. To differentiate a function is to find its derivative. So for this, I started easy. This is a power of x, so I'm just going to use this rule. So the 3 comes down and I reduce it, so 3x squared. Okay, so what about something slightly more complicated like this? This is just as easy because these constants can carry right through. Because what do I do if I have a constant times something? The a just carries right through like this. So if I'm differentiating this, the 2 carries right down. And then I'm going to write, what is the derivative of x cubed? Well, that's 3x squared. That's the same thing we got just a second ago. And then I keep moving, so addition and subtraction can come right down. So this minus sign comes right down. This 3 comes right down. When I do the derivative of x squared, that's like this again. So I can write 2x to the 1, right? Similarly here, the 7 comes down, And this x, it's like x to the 1, right? So I can treat this like a power of x. So I would go 1 x to the 0 minus, and then this part is only a constant. The derivative of a constant is just 0. Okay, and I just need to simplify that. So this is 6x squared minus 6x. X to the 0 is just 1. In fact, you can just remember the derivative of x is just 1. And that's what happened. This is x. Its derivative was this, which is just 1. So here's my answer. Okay, so let's keep going. What about this function? So here we see an e to the x, which we haven't seen before, but remember we have this rule. Also, what do I do with the square root of x? Actually, the square root of x is a power of x. It's the same as x to the 1/2. So you might have to do this. You might receive a function that has square roots or even cube roots, and then you have to change that to a power, so then you can use this rule, right? So, okay, so knowing that, let's do the derivative. The 3 carries right down. The derivative of e to the x is just e to the x. So, there. And the derivative of x to the 1/2 is, okay, so I'm doing this rule. So I go 1/2 x to the, and actually it's tempting to do this in my head, but let me write. It would, the new power would be 1/2 minus 1, right? Which is, of course, negative 1/2. When you do calculus, you get really good at subtracting 1 from fractions because you end up doing it a lot, just like this. Here's a fraction 1/2, and we had to subtract 1 from it. So you'll get good at this as we go. Anyway, what about part D? Part D is just like maybe like a harder version. This is involving cube roots and also a square root, and also this is involving division, which we have not dealt with any division yet. Let me tell you what I'm going to do. I'm going to convert everything to powers of x. This one is x to the 1/3. This one is x to the 1/2, which is, okay, I'm taking a power of x divided by another power of x, so the thing to do is subtract them, and keep in mind 1/3 minus 1/2. I have to get a common denominator here. That's 2/6 minus 3/6, negative 1/6. So when I divide these, I get x to the negative 1/6. When I divide these, so I would get 10 minus 1/2, which is 20 halves minus 1/2, so 19 halves. Okay, so it's ugly fractions, but it is what it is. The derivative, I just use my rules. So negative 1/6 x to the, okay, now we have to get good at subtracting 1 from a fraction. If I have negative 1/6 and I'm about to subtract 1 from it, it's like subtracting 6/6, so I would have x to the negative 7/6. Negative 1/6 minus 1 is negative 7/6. Minus 7 times, okay, 19 halves x to the, okay, we have to be good at subtracting 1 from fractions. I'm subtracting 1, which is like 2 halves, so 19 halves minus 2 halves would be 17 halves. And sorry, but I just realized I got myself into a little trouble. I'm sure I can figure out what 7 times 19 is by hand, but I just cheated and used the computer because I want to simplify this. This is negative 1/6 x to the negative 7/6 minus 133 over 2 x to the 17 halves, like that. So that's my fully simplified answer. So it's a little ugly, and I had to do 7 times 19 to figure it out, but it's not that bad. Okay, so let's do the next one. So for the next one, this is a trap, and it's a particularly tempting trap because I know I just got a rule for e to the x, so I'm tempted to say, I mean, maybe this the derivative of this should be itself or something like that. But let me explain the trap. This is a constant. How do I know? The letter x just doesn't appear here at all. You know, these functions that we do the derivative of, they involve the letter x. Like, you know, depending what number x is, x cubed is a different number for different values of x. This is always the same number, no matter what x is, because x just does not play any role in this expression. So, in fact, I could even change the question. I mean, I could just put some more stuff. Why don't I multiply it by 170 and then add 235? I mean, it doesn't matter what I do, as long as the letter x is not appearing here, this is all just a constant. So the derivative of a constant is 0. So don't be tricked. Constants can appear complicated, like this appears to be a somewhat complicated expression, but the point is there's no x's in it, so the derivative is just 0. Okay, so that brings us to tangent lines and then normal lines. I'll explain what that is. If you remember, we talked about tangent lines before too. The tangent line is just a line whose slope is the derivative. Now that we have shortcuts for finding derivatives, it's going to be easier to find tangent lines. So why don't we find a tangent line to this? So I'm going to find the derivative, and I'm going to call the derivative y prime, just like how we call the derivative of f of x, f prime of x. So the derivative is, remember how we talked about the derivative of x is 1? That came up over here when I was doing this derivative. When you use the power rule to do the derivative, you just get 1x to the 0, which is 1. So, yeah, I encourage you to just remember that. The derivative of x is just 1, and the derivative of e to the x is e to the x. So this is y prime. So the slope of my tangent line is, it's given by the derivative, but I have to plug in the right point. So this is the x and y coordinate of the point that I'm finding the tangent line to, so I'm going to plug in the x coordinate for x. So I get 1 plus e to the 0. E to the 0 is 1, so I just get 2. And now I'm looking for a line with a slope of 2 that goes through this point, and that's easy enough. And I can leave my answer this way if I like. Yeah. So we were also told to find the normal line, and I haven't told you what that is yet. It's actually easy. The normal line is just perpendicular to the tangent line. In math, often, and not always, but it's often that you'll hear the word normal meaning perpendicular. And this is not the first time you'll hear this. The word normal, of course, we overuse the word normal to mean many different things, but one very common use is that it's perpendicular to something. So the normal line is just perpendicular to the tangent line, and it should go through the same point. So actually, I don't have to do any more work. Well, I have to write down my answer, but this is hardly work. The slope of the tangent line was 2, so to be perpendicular, I do the negative reciprocal. That's how you do a perpendicular slope, is the negative reciprocal of the original slope. And now I know I want a line with this slope through this point. So it's like writing this down again, except with a different slope this time. So I'm like that. Okay, good. Let me do one more example. And this is relevant to tangent lines again. Oops, we're blurry. There we go. So I have this curve. It's a parabola, y equals x squared minus 4x plus 10. And I want to find points where the tangent line is, okay, for part A it says horizontal. Keep in mind, horizontal just means slope of 0. The slope of the tangent line is the derivative. So I'm going to find the derivative and set that equal to 0. So the derivative of x squared would be 2x to the 1, using the power rule. The derivative of negative 4x, keep in mind the derivative of x is just 1, so the derivative of negative 4x is just negative 4. This 10 disappears, because this 10 is a constant all by itself. So here's the derivative. It's just 2x minus 4. And what did I say I was going to do? Since I'm looking for a horizontal tangent line, I'm going to take the derivative, which is the slope of the tangent line, and I'm going to set it equal to 0, which is the slope that it would be if it was horizontal. And now I just solve for x. I get x equals 2. And at this point, I want to look back at what the question actually asks and make sure that I answer it properly. What I found was an x-coordinate. What the question asks for is a point on the curve. So the point is, well, I found the x-coordinate. The y-coordinate is just whatever I get from plugging this in. And I guess if I put in 2, I get 4, yeah, maybe. Make sure I don't make a mistake. 4 minus 8 plus 10. So actually it looks like I get 6. Okay. Part B is where I want to find a point where the tangent line is parallel to this line. So let's not think too hard or get confused. to be parallel to this line just means it has the same slope. Let's find the slope of this line by solving for y. I get y equals negative 2x plus 1, which means the slope is this negative 2. So this is going to be a lot like part A, except instead of looking for a slope of 0, this time I'm looking for a slope of negative 2. So I'm going to find the derivative, but actually I already found the derivative last time. And I'm going to set that equal to the slope I want, which is not 0 anymore, it's negative 2. And now I solve for x. So 2x equals 2, x equals 1. And then I do the same thing. This is the x coordinate, but the question asked me for a point. So the point has that x coordinate, and the y coordinate is whatever I get from plugging it in. 1 minus 4 plus 10 is, I guess, 7. So there we go.